In the first part of chapter 10, we have discussed the torque and relation between torque and force, and we have discussed the translational and rotational motion in a motion of a wheel of a car, for example, and we have discussed this type of motion in terms of kinetic energies, and we have discussed this type of motion in terms of dynamics, net force acting on the system and net torque acting on the system. And now we will continue with the work in rotational motion, and then we will continue with the power, and we will learn angular momentum. You have learned linear momentum in the past, and now we will today learn the angular momentum, and finally we will finish with the conservation of angular momentum, and we will also talk about gyroscopes, motion of gyroscope. So let me start with the work in rotational motion. Here you see a child. This child applies a tangential force on this rotating object, and with this force she can produce a torque acting on this object. Okay, so here on the right side we have sketch. This is the merry-go, okay, this one, and by applying this tangential force, this child can produce this displacement. Displacement is ds, and this ds can be written in terms of r and d theta. So the displacement is given with here r times d theta. Maybe I should use the pen. Okay, this is the displacement ds, and the work done by this tangential force is given with this expression. Work dv is equal to F tangential times displacement ds. So just take this ds and put it there. Finally, we have this work, okay, F tangential r times d theta. Here, what do you see? F tangential times r, this expression. Look at this expression. What is this? This one, F times r, lever arm to the rotation axis. This is the torque, right? This is the torque. Then I can write the work like this. The work done by the F tangential is equal to torque times dt, the change in the angle, okay? So now let's try to write this one in a general form. This is the lower limit, initial angular position, and this is the upper limit here, theta 2, final angular position, and we have work. Here we have dv. If you integrate this one and this one, and on the left side we have work, and here on the right side we have this integral. Just consider that this torque is constant. Then you can take this torque out of this integral, and if you solve this integral, lower limit theta 1, upper limit theta 2, d theta, then it is equal to theta 2 minus theta 1, or it is delta theta. Okay, so this is the solution of this integral. And then work can be written in this expression, torque times delta theta. Okay, if the torque is constant. And work depends on the torque times angular displacement. Okay, here we have torque times d theta. Okay, in the previous lecture we have learned that the torque is given with I times alpha z. I is moment of inertia, alpha z is the angular acceleration. So here we have d theta. So what is this alpha z? Alpha z is angular acceleration, and angular acceleration is given with this expression, time derivative of angular velocity. Okay, so instead of alpha z, just use this expression in this equation, and then here we have d theta, just here we have d theta, here we have dt. Just take this one. Take the omega z here alone, and then here we have d theta over dt. So what is this? This is angular velocity, right? We have done it in chapter 9. This is the angular velocity. Now here we have moment of inertia, angular velocity, and the omega z. Okay, we have this expression. Let me clean this part and continue. Then, instead of torque times d theta here within this integral, just use this expression. Take this one, put in this integral. Then here we have V work total work done on a rotating rigid body, work done by the net external torque, okay, can be written in this form. Now we have lower limit change from theta 1 to omega 1, because here we have omega z, and the final limit is omega 2. What is omega 1, omega 2? This is the initial angular speed. This is the final angular speed. Moment of inertia, omega z, d omega z, okay? If you solve this integral, you can get this expression. So we have this one. Let's consider moment of inertia is constant just for this one, okay? This has certain I moment of inertia about this rotation axis, and this is constant, let's say, okay? Then take this I out of integral, and here we have this one, omega 1, omega 2, omega z, and d omega z. If you solve this integral, then you will get this one. Here we have I, and here we have omega z square over 2, limits from omega 1 to omega 2. Then if you also solve this one, then finally you will get this expression. 1/2 I omega 2 square minus 1/2 I omega 1 square. So what is this? 1/2 I omega square. This is the rotational kinetic energy, right? Which we have learned during the last lecture, and we have also discussed in chapter 9. This is the final rotational kinetic energy. So you can say K2, final rotational kinetic energy, minus, this is the initial rotational kinetic energy when the angular speed is omega 1. Then what is this? This is delta K. Do you remember? This is similar to the work energy theorem. Total work done on a rotating rigid body is equal to the change in its rotational kinetic energy. Okay? So we have this conclusion. Total work done on a body by the torque is equal to the change in rotational kinetic energy of the body. This is the initial rotational kinetic energy of the body on the right side, and this is the final rotational kinetic energy of the body on the left side. And the change in the rotational kinetic energy gives us the total work. Any question here? Let me find a relation between work and power in rotational motion. So we have this work, which we have found this relation here, okay? Here we have a merry-go, we applied a tangential force, and we have produced a ds displacement, and finally the work done by this tangential force is given with torque times d theta, okay? Just continue from this expression. If you take time derivative of both sides, so time derivative of work, and here on the right side, if you consider that the torque is constant, then take the time derivative of d theta. So what was d theta? D theta is the change in the angular position, right? So if you take time derivative of angular position, then we can get the angular speed, right? So this gives us the angular speed, And what is this? Time rate of work. This is power, okay? So we have learned this one in the previous lectures. So on the left side, we have power due to a torque acting on a rigid body. And here we have a torque. And here we have angular velocity of body about certain rotation axis. This is the power due to the torque. And what we have here we have torque times angular speed. And remember the power which we have learned in chapter 6 for a particle motion. This power is given with force times velocity. So they look very similar. As I told you, if you know the previous information from the previous chapters, then you can find a relation between the linear motion and rotational motion, and you can better understand the topic. So now we have the power due to a torque acting on a rigid body. So here, let me give you one example. Here, there is a helicopter and it is stationary in the air, okay? Stationary in the air. When a helicopter's main rotor is spinning at a constant rate, positive work is done on the rotor by the engine and negative work is done on it by air resistance, okay? So there is the air resistance. So the work done by a torque applied by the engine is given with this one. And there is also work done by the friction force, air friction, okay? Then, hence the net work being done is 0 and the kinetic energy remains constant, okay? So look at the V total, the total work done on a rigid body, final kinetic energy minus initial kinetic energy. If the angular speed is constant, okay, in both cases, then the change in the kinetic energy is 0. Then the total work done on a rotating body here is 0. So this is example for helicopter application. And now let me continue with the example from the book, example 10.8, calculating power from torque. An electric motor exerts a constant 10 Newton-meter torque on a grindstone, which has a moment of inertia of 2 kilogram times meter square about its shaft. This system starts from rest. Find the work done by the motor in 8 seconds and the grindstone's kinetic energy at this time. What average power is delivered by the motor? So the torque is given, okay, here, net torque is given, and moment of inertia of the grindstone is also given, okay? And if you apply this one, net torque acting on this grindstone is given I times alpha z, angular acceleration, and I is given, net torque is given. You can calculate angular acceleration, 5 radian per square second. So what was the question? Find the work done by the motor in 8 seconds and find the grindstone's kinetic energy at this time when the time is 8 seconds. So how to find the work? In order to find the work, you can use this expression, torque times delta theta. Just remember this expression, work torque times delta theta or d theta, okay? So what is delta theta? This is the change in the angular position, okay? And how to calculate delta theta? During the chapter 9, I have explained that if the angular acceleration is constant, then you can apply equations which we have learned in chapter 2 for constant acceleration, okay? Please look at the chapter 9 and you will remember this one. So if we have a constant torque, then here we have a constant angular acceleration. And if we have constant angular acceleration, I can write this expression, final theta position minus initial theta position namely delta t, is equal to 1/2 alpha z t square, okay? Like we have done in chapter 2 for the linear acceleration, for the constant acceleration. Then time is given 8 seconds, put the time here, alpha z here we have calculated, put it there. Then you can calculate delta theta, the change in the angular position, which is given with 160 radian, and put this information into the work equation. Then torque is given, then we can calculate the total work done on this grindstone, which is given with 1600 joule. Okay, so we have found the work, and what about the kinetic energy? In order to find the kinetic energy, you can use this relation on the left side. Kinetic energy is given with 1/2 I omega z square. So I know the I. What about the omega z, angular velocity? We have calculated angular acceleration. If you use this expression for the constant angular acceleration, you can calculate the angular velocity for when the time is 8 seconds. So then angular velocity is given with 40 radian per second, and just use this angular velocity within this rotational kinetic energy, then you can find 1600 joule. So what was the initial rotational kinetic energy? The system starts from rest, so initial rotational kinetic energy was 0. This is the final rotational kinetic energy when the time is 8 seconds, okay? So what about the work? The work done by the torque when the time is 8 seconds is also 1600 joule. So the total work is equal to the change in the rotational kinetic energy. And the last question, what average power is delivered by the motor? The average power is given with delta work over delta t. Delta t is 8 seconds, delta work is given, then you can calculate 200 watt. This is the power when the time is 8 seconds. So now let me continue with the angular momentum. Do you have any question with this example? Be careful with this part, angular momentum. In the previous chapters, we have learned momentum, or you can call it linear momentum, okay? So we will have more or less same way, okay, to calculate the angular momentum. In the past, we have investigated the relation between linear momentum and force, and here today we will investigate the relation between torque and angular momentum. So torque is given with this expression. We have done it, okay? This is the distance to the rotation axis. This is the applied force, and this is the torque produced by this force. And the angular momentum of a particle is given with this expression. Position vector of particle relative to origin, rotation axis. And here we have linear momentum of particle. And from the previous chapters, we know that linear momentum is given with m times v, right? Then we have angular momentum in terms of velocity. So what about the unit? The unit of position vector is meter. The unit of this mass is kilogram. The unit of this velocity is meter per second. Then the unit of the angular momentum is kilogram times meter square per second. So now let me show you the direction of the angular momentum and how to calculate this one. So we have given this expression. So angular momentum is given with R cross product mv, or R cross product p, okay? So here we have mass of m, and this z is the rotation axis, and this mass has certain distance to this rotation axis, which is given with r, okay? And then this is the momentum of the particle. and momentum of the particle is given with m times v. And what about the angular momentum of the particle? Angular momentum of the particle is given with p times lever arm. Okay, p times lever arm. So what is p? P is mv, put it there. Lever arm is given with L, put it there, mvl, okay? Or you can write this one, m times v times r times sinus phi, or you can write in this form. This is the perpendicular component of the momentum to the lever arm or position vector here, and this is the distance to the rotation axis. Then if you multiply both quantities, then you can also calculate this angular momentum. And the direction of the angular momentum, look at the vector product here. Here we have r vector product mv. So we have the direction of the position vector, and here we have direction of the momentum vector. And if you use the rule, right-hand rule, then you can calculate that, you can find that the direction of the angular momentum of the particle is along the z-axis. Okay, so we have position vector in the xy plane, we have momentum vector in the xy plane, but the resultant angular momentum vector is perpendicular to the xy plane. It is along the z-axis. So now let me continue with some different conditions in angular momentum. So let's consider that we have a net force acting on the particle, and due to this net force, the particle's velocity and momentum change. Okay, then its angular momentum may also change. So look at the angular momentum. If you change the velocity, then you can change the angular momentum. Okay, so just use this expression, this one. Look at this one. Angular momentum, let me write this one here. Angular momentum is given with position vector cross product mv. So if you take time derivative of this one, so time derivative of the left side and time derivative of the right side, probably you have learned how to take the time derivative of the vector product. In order to take the time derivative of the vector product, first of all, you will take the time derivative of this part cross mv plus time derivative of this part cross r. Okay, this is the rule which you have learned. Then just come to the solution. Here we have dr over dt, time derivative of the position. What is this? Time derivative of position is velocity, right? Then just put this velocity here. And we have velocity here, we have velocity here. If we have cross product here, this result will be 0, okay? Because in cross product, we have this one, v times sinus 0, okay? Because they are same vectors and the angle between the same vectors is 0, then sinus 0 is 0, then this will give us 0. Then this time derivative of the angular momentum will give us this expression on the right side. Here we have ma. What is this ma? This is the force, right? Then I can write this time derivative of this angular momentum is given with r times f. So what is this? This is torque. Okay, now I have relation between the angular momentum and torque. So the rate of change of angular momentum of a particle equals the torque of the net force acting on it. Remember the chapter 8, the rate of change of linear momentum of a particle equals the net force that acts on it. So this expression from the chapter 8, dp over dt, this is the force. Okay, so what we have here, dl over dt is the torque. Okay, so if the net force is 0, then the momentum is constant. Okay, we have learned this one during the chapter 8. Here, if the net torque is 0, then angular momentum is constant. Now I will discuss this situation. Let me continue with the rigid body, and to find the total angular momentum of the rigid body, let's consider this is the rotation axis, and this rigid body with this shape is rotating around this rotation axis, around the z-axis. It has certain angular speed, okay? And what is the total angular momentum of this rigid body? So just choose a particle here with the mass mi, and it has distance to the rotation axis, to the O position with ri, and it has tangential velocity vi, which is given with ri times omega. We know this information from the last lecture. So linear velocity has this relation with the angular velocity. Okay, and what about the angular momentum of this ith particle? Angular momentum direction is this one, okay, and it is given with this expression. We have done it here, okay. Angular momentum is given with mv times L, or r times mv, or r times p. So look at this one, mv times L. Instead of L, we have ri, the distance to the particle from the rotation axis. So instead of vi here, I can use this expression, okay, ri times omega. Just take this expression, put it there, so I can calculate Li, the angular momentum of the particle here. Then it is given with mi ri square omega, okay? So each particle in this rigid body has this angular momentum. In total, we have many particles. We have many particles on this rigid body. So in order to find the total angular momentum of this rigid body, then collect all angular momentums, okay? So what we have here, this is the moment of inertia. This is the angular speed. So then I can write this angular momentum I times omega, okay? Remember the linear momentum, P m times v, okay? This is the angular speed. This is the linear speed. This is moment of inertia. This one, this is the mass. This also includes mass, okay? This is the angular momentum. This is the linear momentum. You see, you can make analogy. Okay, now we have angular momentum of a rigid body rotating around symmetry axis is given with this expression, okay? I times omega. This is the angular velocity. And for a system of particles, the rate of change of total angular momentum, this one, dl over dt, equals the sum of the torques of all forces acting on all particles. So which we have done it here, this one, this expression. The torque is given with dl over dt, or the rate of change of angular momentum is equal to the torque of the net force acting on it. Okay, so these two equations are very useful. Okay, so remember the previous chapters, the net force is given with this expression. Okay, it is similar. And remember the previous chapters, linear momentum is given with this expression. It is similar. So now let me continue with the relation between angular momentum and angular velocity. So they are in the same direction. Again, you find the direction of the angular momentum with the right-hand rule. So depending on the rotation direction, counterclockwise or clockwise, by using the right-hand rule, you can find the direction of the angular momentum. You can find the direction of the angular velocity. Okay, so this is the direction of the angular momentum. And here, let me give you another information. Let's consider that a system of particles, many particles in a rigid body rotating about symmetry axis, then the angular momentum is given with this one, okay, I times omega z. And let's consider that the body is a rigid body and it is rotating about symmetry axis and the rotating axis does not change, then this moment of inertia is constant, okay? Then if this axis has a fixed direction in the space, it means that the rotation axis does not change. Then the vectors, this angular momentum vector and angular velocity vector, change only in magnitude, not in direction. Their directions do not change, but their magnitudes can be changed, okay? So here, look at this expression, dLz over dt. Here we have Lz, which is given I times omega z, and here you can do this one, d omega z dt. So what is this one? Time derivative of angular velocity. This is the alpha z, angular acceleration. Then I can write this one, I times alpha z, right? What is this? The time rate of the change in the angular momentum. This is the torque, okay? Then on the left side, I have torque. On the right side, I have this expression. And do you remember this formula? So we have this one. But if the body is not rigid, if the shape of the body changes during the rotation, then if the shape changes, this moment of inertia may change, okay? If the moment of inertia changes, look at this equation. If this moment of inertia changes, then this angular momentum changes, even if the angular speed is constant, okay? If we don't have a rigid body, if the body is not rigid, then this may change, this moment of inertia may change. Then even if this is constant, this angular momentum can be changed due to the non-rigid body. Do you have any question? Okay, here I will discuss another situation. Be careful. Up to now, we have considered that the rotation axis of the body is a symmetry axis. But what happens if the rotation axis of a rigid body is not a symmetry axis? Then angular momentum does not in general lie along the rotation axis. So here we have a body and the rotation axis is this one. It has certain angular speed, but this rotation axis, this one, is not the symmetry axis. The body is not symmetric around this axis, let's say, okay? So what happens to the angular momentum in this case? In this case, the direction of the angular momentum will change, okay? Even if angular speed omega is constant, the direction of angular momentum L changes and a net torque is required to maintain the rotation, okay? So just consider this one, L is constant. If L is constant, what is the time derivative of a constant number? Time derivative of constant number will be 0 if L is constant, okay? But if L is not constant, then the torque will be different from 0. You need certain torque. This is valid for the wheels of the cars. If there is some damages on the wheel of the car, this angular momentum can be changed during the rotation. Then this will fight against the rotation. In order to keep the rotation, you have to apply a net torque, okay? This is special condition for the angular momentum. And now let me continue with the example 10.9, angular momentum and torque. A turbine fan in a jet engine has a moment of inertia of 2.5 kilogram meter square about its axis of rotation. So moment of inertia is given. As the turbine starts up, its angular velocity is given with this expression. What do you see here? That the angular velocity depends on the t square. So as a function of time, angular speed increases. Find the fan's angular momentum as a function of time. So fan's angular momentum as a function of time, let's say, okay, and find its value when the time is 3 seconds. What is the angular momentum when the time is 3 seconds? Find the net torque on the fan as a function of time and find its value when the time is 3 seconds. So what is the torque as a function of time and what is the value of the torque when the time is 3 seconds? So how to do that? Angular momentum is given with I times omega. Moment of inertia is given, okay? And angular speed is also given within the question. Look at this one. Then put it there. So now we have relation for the angular momentum in terms of time. So when the time is 3 seconds, just take 3 seconds here. Then you can calculate the angular momentum, 900 kilogram times meter square per second. In the second question, torque is asked, and torque is given with this relation, time derivative of angular momentum, right? So we have calculated angular momentum in terms of time. If you take time derivative of this expression, then you can get this expression here, okay? And if you put 3 seconds instead of time here, then you can calculate the torque when the time is 3 seconds. It is 600 Newton meter. Do you have any question here? Then let me continue with the conservation of angular momentum. I have already given some information about this, but here let me discuss in detail. So we have found this relation, right? Net torque acting on the rigid body is given with dl over dt. So if the net torque acting on the system is 0, then what about this one? This is also 0. But what about L? L is constant. Or vice versa. If L is constant, the time derivative of a constant number is 0, okay? So then we come to this conclusion. When the net external torque acting on a system is 0, there is no net torque, then the total angular momentum of the system is constant or conserved. This is the conservation of angular momentum. If the net torque is 0, total angular momentum is conserved. And this is very helpful information when you are solving the questions in chapter 10. Okay, if the net torque is 0, then this is 0 and angular momentum is constant. So in the previous transparencies, we have calculated that angular momentum is given with moment of inertia times angular speed, omega, okay? So if the angular momentum is conserved, I can write this expression. This is the initial angular momentum of the system. This is the final angular momentum of the system. If the angular momentum is conserved, I can write this one. I1 omega 1 is equal to I2 omega 2. Sometimes moment of inertia changes during the rotation, during the condition, okay? And if this moment of inertia changes, then this angular speed changes. Here you have different moment of inertia, different velocity, but I times omega angular momentum is constant. So L1 is equal to L2. So this equation must be equal to this one, okay? If there is no net external torque acting on the system, this is the conservation of angular momentum and very helpful information in chapter 9 and chapter 10. Remember the conservation of momentum in the previous chapters, okay? So when you are solving some problems, you use the conservation of momentum. Sometimes you use the conservation of energy. And here within this chapter, you can use the conservation of angular momentum if the net torque acting on the system is 0. Now, let me discuss another situation with the angular momentum. Here we are discussing the external torques, okay? Net external torques. What about the internal torques? Actually, we have discussed this one in chapter 8, okay? 2 astronauts, and they are isolated from the external sources and they are applying force on each other, okay? Suppose a body A exerts a force on B, the corresponding torque with respect to whatever point we choose is this one. Torque applied by A on B, okay? Then this torque can be written like this. This produces a change in the angular momentum of the B body, and at the same time, the body B exerts a force B on A with a corresponding torque B on A, okay? Then this torque can be written like this, and it can produce a change in the angular momentum of the A object. Look at this one. And what about the forces here? The force applied by A on B is equal to minus force applied by B on A, okay? So due to the Newton's third law, action-reaction pairs, okay? Then if we have this relation, then we have this relation, okay? Torque B applied on A is equal to minus torque A applied on B. Then what about this one? This is LA over dt. This is dLB over dt, change in the angular momentum of B. This is the change in the angular momentum of A. So since they have opposite signs, if you take them like this, torque B on A plus torque A on B equal to 0. And then I can write this expression. Okay? What do you see here? This is the change in the angular momentum of the A body. This is the change in the angular momentum of the B body. But what about the total change in the angular momentum of the system is 0. Okay. Why? Because this force acting on A, this force acting on B, these are the internal forces. Okay. Internal forces cannot affect the system because they are equal to each other. They are action-reaction pairs. So since there is no external torque, okay, there is no net external torque acting on the system, the total angular momentum of the system is conserved. Okay. So when you are dealing with the conservation of momentum, you always look at the net external torque produced by the external forces. Okay, internal forces, the effect of the internal forces on the net torque on the system is 0. Okay, internal forces cannot change the total angular momentum of the system. So the total angular momentum of the system is constant. The torques of the internal forces can transfer angular momentum from one body to other, but they can't change the total angular momentum of the system. Here we have one example. This is the cat. It is sitting here and then it is falling down. Okay, what happens? So during this falling, cat pivots different parts of its body in different directions. Okay, so then it lands feet first. At all times during this process, the total angular momentum of the cat as a whole remains 0 because the net torque acting on the cat is 0. Okay, net external torque. So there are some internal changes. Okay, so there are, if you consider this is a system, so there are some internal changes in the system, but since there is no external net torque, then total angular momentum is conserved. Okay, this is a bio application, let's say. And now let me finish this part with 2 examples, and then I will continue with the gyroscopes. So conservation of angular momentum. This is the example from the book. A physics professor stands at the center of a frictionless turntable with arms outstretched and a 5-kilogram dumbbell in each hand. So this is the initial condition. Okay. Professor here, and this is turntable, this one, and these are the dumbbells. Okay, and this is the professor. So he is set rotating about the vertical axis, making 1 revolution in 2 seconds. Okay, so let's say a student rotated this professor around this axis, and then he has certain angular velocity, which is given 1 revolution in 2 seconds. Okay, find his final angular velocity if he pulls the dumbbells inward to his stomach. In the second condition on the right side, look at the dumbbells in the first case. Look at the dumbbells in the second case. So he collected dumbbells here, and this is the rotation axis again. And the question, what is the final angular speed, angular velocity? His moment of inertia without dumbbells is 3 kilogram times meter square with arms outstretched, and 2.2 kilogram times meter square with his hands at his stomach. Okay, so this is the initial moment of inertia. This is the final moment of inertia of the professor, okay, for both conditions. Remember this formula, okay? What do you see here? the mass in this case collected here, but here in the first case, mass is distributed far from the rotation axis, okay? Then he will have different moment of inertia. Don't forget this one. Then the dumbbells are 1 meter from the axis initially and 0.2 meter at the end. Okay, so now let's try to solve the question. The moment of inertia of the system, professor and dumbbells, is given with this one, I professor plus I dumbbells. Okay, so this is the moment of inertia in the first case. This includes I professor plus I dumbbells. This is the moment of inertia of the professor, which is given in the question, okay, for the first condition, plus dumbbells. This is M, this is R, 2mr squared, because we have two dumbbells, okay, at the beginning. Then this is the initial moment of inertia of the system, professor plus dumbbells. And what about the initial angular speed? 1 revolution per 2 seconds. It is 0.5 revolution per second, okay? Then what about the final moment of inertia? The final moment of inertia of the professor and the final moment of inertia of the dumbbells. Look at the R here in the first case. R is 1 meter because the distance of the dumbbell to the rotation axis is 1 meter in the first case. In the second case, distance is 0.2 meter. Then R is changed. Then the contribution to the moment of inertia from the dumbbells will be changed. Then this is the final moment of inertia of the system. And now you can apply conservation of angular momentum. Because there is no net torque acting on the system, L1 is equal to L2, then I1 omega 1 is equal to I2 omega 2. Then if you take omega 2, which is asked in the question, then you can get this expression. Put all these things into the equation, then you can find the relation for the final angular speed of the system. Okay, now let me continue with this example 10.11, a rotational collision. Here on the right side, we have a figure which shows two disks, an engine flywheel A, this is A object, this one, and here we have a B object, a clutch plate B attached to a transmission shaft. Their moments of inertia are IA and IB initially. They are rotating with constant angular speeds omega A, omega B respectively at the beginning. We push the disks together here in this final condition with forces acting along the axis so as not to apply any torque on the either disk. Okay, you apply force in this direction. You apply force in this direction and you put these two objects together, okay? But this is rotating around this axis, this is rotating around this axis, so these forces cannot produce any torque, okay? Because they have line of action along the rotation axis, their lever arms are 0, then these forces will not produce any torque, okay? Then the net torque around the rotation axis, net external torque around the rotation axis is 0. Then if you apply this rule, then the angular momentum is conserved, angular momentum is constant, then initial angular momentum of the system is equal to the final angular momentum, okay? So what about the initial angular momentum? Initial angular momentum is given with angular momentum of the A object plus angular momentum of the B object. And what about the final angular momentum of the system? The total moment of inertia of two objects because they are rotating together, they have same angular speed, and put the angular speed here. Then if you take the angular speed, you can get relation for the angular speed, final angular speed. Do you have any question? Okay, let me continue with the gyroscopes and precession motion. Here you see a gyroscope. This is the pivot, and this gyroscope is rotating around this pivot. But within the gyroscope, you see a wheel with the green color. I think you can see this wheel with the green color is also rotating another axis. Okay, it is like this. We have a pivot, this black one here, okay, and this is the flywheel, and this flywheel here with the green color is rotating around this axis with some certain angular speed, and the total system is also rotating around this rotation axis. Okay, this is another rotation axis, and this is the rotation axis of the flywheel. So what we have here, the angular speed of the flywheel, which is rotating around this axis, is given with omega, and the angular speed of the complete system rotating around this rotation axis is given with omega. Okay, so the circular motion of flywheel axis is called as precession. Okay, so this is also rotational motion. Okay, please try to understand this motion. Here we have two different rotational motion. One is the rotation of the flywheel, this green color. It is rotating around certain axis, and the complete system has a precession motion. It is rotating around this rotation axis. Okay, if you understand this motion, the rest is easy. So first of all, let's consider that this flywheel here on the right side is stationary. Okay, so it is not rotating. They will fall to the table surface. Okay, if this flywheel is not rotating, this will fall to the surface of the table. When the flywheel spins, this one, if this flywheel is rotating around this flywheel axis with some certain angular speed, it and its axis float in the air while moving in a circle about the pivot. So if this flywheel is stationary, it will go down and it will stop. But if this flywheel is moving with some certain angular speed, then it will travel around this pivot with some certain circular motion, which is given with precession. Then let's investigate. At the beginning, the flywheel is at rest. If a flywheel is initially not spinning, its angular momentum is 0. So look at this one. This is the rotation axis of the flywheel, but it is not rotating, okay? It is stationary. Then this is the x-axis, this is the y-axis, this is the z-axis. Let me show with the pen. This is x-axis, this is the y-axis, this is the z-axis. And at the beginning, omega x is 0. So this flywheel here, shown with orange color, let's say, okay, is 0. Then the angular momentum of the flywheel is 0 because it is not rotating. So what about the forces acting on this flywheel? There is a weight of the flywheel. Let me show you with different colors. This is the weight of the flywheel, okay? And this is the normal force applied by the pivot, okay? And what do you expect? This is the lever arm for the weight. And if you consider this is the rotation axis, this flywheel will move like this, okay? it will rotate around this axis, okay, and it will go down. When the flywheel is not rotating, its weight will produce a torque around the pivot. So let's try to write this torque. This is R, this one, the distance to the rotation axis, and this is the force applied by the weight. So this torque will produce this type of movement, okay, causing it to fall along a circular path until its axis rests on the table surface. Did you understand this part? If you have any question related to this part, please let me know. So this was the condition for the non-rotating flywheel, okay? Then let me investigate what happens if I look from the top of the flywheel for this first condition when the flywheel is not rotating. So now we are looking from the top. This was the x-axis, this was the y-axis, this was the z-axis, and now I'm looking from this side. Okay, I'm looking from this side. So this is the x-axis, this is the y-axis. Now z is along this direction, and this is the flywheel. Okay, so look at this one. There is a weight downward, and there is r position vector, and the torque is given with this one. By using right-hand rule, you can get that this is the direction of the torque, okay, along the y-axis. This is the direction of the torque, and this flywheel is moving like this, rotating around this pivot and goes down. So finally it will look like this. This is the pivot, let's say, and this is the flywheel. This is the ground, okay? At the beginning it was here. And it moved like this. So during this moment, there is a torque acting on this flywheel with this expression. I think it is clear. Now we are looking from the top for this condition. So we know this expression, dl over dt is equal to torque, right? Then if I take dl from this expression, which is given with torque times dt, right? I have a constant torque acting on the flywheel due to the weight here. This is the torque, okay? But what about dt? For each time interval, I have different dl, okay? So for the first time interval, I have dl in this direction. The direction of the angular momentum is along the direction of the torque. And this is the dl for some certain dt time. And for some certain dt time, I have another dl. And for some certain dt time, I have another dl. For some certain dt time, I have another dl. And for some certain dl, I have another dl, okay? At the beginning, L was 0, and just about the touch on the surface, we have angular momentum, this one. This is the final angular momentum, okay? It is increased by time with this expression. So if you increase the time, dl increases. In falling, the flywheel rotates about the pivot and thus acquires an angular momentum. The direction of L stays constant. So the direction of the angular momentum is always along the direction of the torque acting on the flywheel. But don't forget that this motion is only about this rotation axis. and the flywheel is not rotating, okay? It is just moving in this direction. But now, let me tell you another condition. If the flywheel is rotating, what will happen? So here we have a flywheel, and now the flywheel is rotating, okay? It has certain angular speed. If the flywheel is rotating, this angular speed is along the x-axis. By using the right-hand rule, you can find it. And it has certain angular momentum associated with the angular speed. So I show it with initial angular momentum of the flywheel. So this is the direction of the angular momentum of the flywheel. It is rotating around this x-axis. Okay? So due to the weight, we have torque acting on the flywheel. I have discussed this one. Okay, here we have a weight, and due to this weight, we have this torque in this direction. Okay. So now what will happen? This is the initial angular momentum of the flywheel. This one, initial angular momentum of the flywheel. And here we have a torque along the y-axis, which is perpendicular to the angular momentum. So due to this torque, we have dl, okay? And what about the total angular momentum? If you use vector sum, here we have initial angular momentum due to the rotation of the flywheel. And here we have dl due to the torque. dl is given with torque times dt. Okay, so torque is due to the weight, and I'm looking from the top. So this Li, initial angular momentum of the flywheel, depends on this one. Li is equal to I times omega x. Let's consider moment of inertia of the flywheel is constant, and angular speed is constant, then this Li is constant in magnitude, okay? So I have constant Li, but I have dl for each time dt, which is coming from the torque due to the weight. For each dt time, I have dl. For each dt time, I have dl, okay? Then what will happen? So due to this dl, this was the initial angular momentum of the flywheel. Due to this dl, I will have this final angular momentum of the flywheel about this pivot origin O, okay? About this pivot. So what happens? This dl changes the direction of the Li. Magnitude of the Li is constant, but its direction changes with this dl. So an additional dl after dt time, so the direction of the Li again changes. So additional dl, Li changes, direction of the Li changes. I am looking from the top. So finally, what will happen? You will see this type of rotation of the Li, okay? So this Li will rotate about this O, this Z rotation axis, okay? So the complete system will rotate about this axis. Now look at this one. This green flywheel is rotating about its certain axis. For this reason, it has certain initial angular momentum, and due to the torque acting on the flywheel due to the weight, it has certain dl, okay? And this dl changes direction of this initial angular momentum, and finally this flywheel is rotating around this pivot. This is the precession motion in gyroscopes. Okay, now let's have a look. So this system is rotating around this pivot, right? Then it has certain angular speed around this pivot, angular speed. So what is the symbol for the angular speed? In the rotational motion, we use omega for the angular speed. But here we have angular speed of the flywheel and we have used omega. So then for this new type of rotation, we use angular speed symbol omega, okay, capital omega. This is small omega, this is capital omega. So here we have omega, angular speed of the flywheel around this axis, around this pivot, okay? So angular speed around this axis is omega, and angular speed about this axis is omega. This is precession motion. So what about this omega? Remember the formula for the angular speed. The angular speed is given with the theta over dt, right? This is the change in the angular position. So let's choose that this is the initial position of the complete system, and now they are here. This is the initial angle phi. Let's say this is the final angle phi 2, okay? And then this is the phi angle. So then in terms of phi angle, this omega angular speed of the precession can be written in this form, d phi over dt. Same, okay? Everything is same. There is no new information here. So what is d phi? Small change in the angle when the flywheel is rotating about this axis, okay? Here we have L, initial angular momentum of the flywheel, and here we have dl, change in the angular momentum of the flywheel due to the gravity, due to the torque applied by the gravity, and this is the rotation of the angular momentum about this axis. Here we have d phi. You see, I can write this d phi with this expression. D phi is equal to dl over L. Okay, this one over this one. This is the d phi. Okay, then this angular speed is given with this expression on the right top corner. Just use it here. Angular speed, precession angular speed is given with d phi over dt. Instead of d phi, just use this expression. And then here we have this one. So what do you see here? What do you see here? dl over L over dt. So what is dl over dt? Just open this expression. Just look at this one. And what is this? dl dt. This is the torque. Okay? Torque around the z-axis. Okay? And this is the Lz. And then instead of torque, we can write this one, I times omega. Instead of torque, we can write this one, weight times R. We have already discussed this one, okay? Then finally, you can write this precession angular speed in terms of torque Z over Lz, or weight times R over I omega. Do you have any question here? This formula is very useful. If you keep in your mind, it will be helpful. If you cannot keep in your mind during the exam, you have to produce this equation. So this precession angular speed around this pivot is given with torque over angular momentum, or weight times R over I times omega. Here, let me discuss some different conditions related to this rotation of flywheel, we have this equation. So what do you see here, that this omega is inversely proportional to the angular speed of spin about the axis. So this is the angular speed about this axis. Let me draw here. Again, this is the pivot, okay? And this is the another axis. This is the flywheel, and this has certain angular speed omega, and this is also rotating around the pivot, and it has certain omega angular speed. And this omega is inversely proportional to this omega. If this omega is huge, then this omega will be very small, okay? A rapidly spinning gyroscope precesses slowly. So look at this one here. So remember the formula. Precession angular speed is given with weight of the flywheel times r, distance to the rotation axis, I times omega. Omega is the angular speed of the flywheel, and this omega, capital omega, is the precession angular speed around the pivot, okay? So if you increase this omega, angular speed of the green flywheel, then this will rotate slowly around this one. Actually, this green one rotates faster, okay? So you can see it. You can also see many videos in the internet related to the gyroscope and precession motion. Now let me continue with the conditions. Another important result of this equation is this one. If you have large angular momentum, then again you will have smaller precession angular speed. And if you apply this rule to the Earth, for example, the precession angular speed of the Earth is very slow, 1 revolution per 26,000 years, okay? The precession angular speed of the Earth, because its spin angular momentum is large, and torque due to the gravitational influences of the moon and sun is relatively small. So here we have small torques acting on the Earth, and angular momentum is huge, then we have very small precession angular speed. And another result of this condition, let me discuss. As a gyroscope precesses, its center of mass moves in a circle with radius r in a horizontal plane. Its vertical component of acceleration is 0, so the upward normal force exerted by the pivot must be equal in magnitude to the weight. So this part is very important, where to discuss it. Let me try to produce an area here and try to draw the motion. Let's consider that. This is the complete system of the flywheel, and this is the origin, and it has a circular motion around this origin, okay? So this is the pivot. And what about the forces acting on the pivot? Look at this one. What about the forces acting on the pivot? Let me use pen here. So there is a weight, okay, acting on pivot, and there's a normal force acting on pivot. Since they are equal to each other, there is no net force along this axis. If you consider this is z-axis, along the z-axis, there is no net force, okay? But this complete system is rotating about this axis. This is a circular motion. In order to have a circular motion, we should have a radial force, right? F radial, or you should have a radial acceleration, okay? So which is explained here. its vertical component of acceleration is 0. So the upward normal force exerted by the pivot must be just equal in magnitude to the weight, which we have discussed. The circular motion of center of mass with angular speed omega requires a force directed toward the center of the circle, right? What about this force? This force is given with this expression. How? The force is given with total mass of the system times A radial. Then instead of A radial, you can write omega squared times R, okay? Remember the angular speed and the relation between angular speed and velocity. So V is given with R times omega. So here, instead of omega, we have capital omega. Okay, so what about the angular acceleration? So we have also a relation between angular acceleration and linear acceleration. Okay, then you can write this expression. If you put it there, finally, the force will be given with this expression. So this force must be supplied by the pivot. Okay. Where is it? This force directed to the center of the circle supplied by the pivot. Okay. Then this flywheel has this type of rotation. Green flywheel is rotating about its axis with some certain angular speed, and the total system is rotating about pivot with some another precession angular speed. This is the gyroscope and precession. Okay, with this one, I have another important information. We have considered that this complete system is rotating around this circular path, right, with some certain angular speed. So if we have this type of motion, counterclockwise motion, if you use the right-hand rule, you should have the direction of the angular speed, and you should have an associated angular momentum, okay? Because angular momentum associated with angular speed is given with I times omega. We have done it, okay? We have done this one. Here, instead of omega, I have another symbol of omega. So we have another component of angular momentum. We did not discuss this one within these calculations. Actually, if this omega is very small, then this perpendicular component of the angular momentum is also very small. Then usually this perpendicular component of the angular momentum is ignored, okay? But sometimes it must be taken into account, and we will not discuss in detail. So now let me finish this chapter with example 10.13, a precessing gyroscope. So look at the question, listen carefully, and you can easily understand, I hope. So here in this figure, figure A, we are looking this picture. Figure A shows a top view of a spinning cylindrical gyroscope wheel. The pivot is at origin. Here we have a pivot, and this is the wheel. We are looking from the top, and the mass of the axle is negligible. So here we have an axle, but its mass is negligible. As seen from above, is the precession clockwise or counterclockwise? So we are talking about the direction of this rotation, okay, counterclockwise or clockwise. Second question, if the gyroscope takes 4 seconds for 1 revolution of precession, what is the angular speed of the wheel? Omega is asked, okay? In the first question, direction of the precession is asked. So just use the right-hand rule and we can find the omega and L. So look at the vector diagram here in figure B. This is the flywheel and this is the weight of the flywheel downward, okay, in this picture pointing into the page, and this is the distance of the force applied by the weight to the pivot, okay, and if you apply right-hand rule, the torque is given here, R vector product weight, and then this is the direction of the torque, okay, applied by the weight. And what about the angular momentum? So the weight points into the page in this top view and acts at the center of mass, and the torque toward the top of the page. This is the direction of the torque, okay? And dl over dt is also toward the top of the page due to the torque. So due to this torque, we have this dl over dt. So angular momentum changes by time. Remember this expression which we have done. Okay, with some certain time we have dl. Okay, this is the delta L. You see direction of the delta L or direction of the dl. It is along the torque. Okay, then what about the rotation of the flywheel? This is the direction of the rotation with some certain omega. If you apply right-hand rule, your 4 fingers will show the direction of the rotation, and then you will have direction of the angular speed, and you will also get the direction of the angular momentum. They will be along the same direction, okay? Then we have omega and angular momentum, and here we have dl, and this is the L plus delta L or L plus delta dl. So then it is rotating like this. If you look from the top, then what is the meaning of this? This rotation is clockwise. So the system is rotating like this. Okay, we have calculated by using this expression. Let me clean this part and then continue with the second part of the question. If you have any question with the first part, please let me know. What was the second question? What is the angular speed of the wheel? Okay, this omega is asked. So we know that this is given with this expression. Weight R over I omega, okay? And if you take omega from this expression, then you can get this expression. Weight is given, R is known, and what about the I? Moment of inertia for the cylindrical shape, you can use this expression, moment of inertia for the cylindrical shape. R is given, M is given, okay? And here we have omega. What is omega? Omega is given if the gyroscope takes 4 seconds for 1 revolution of precession. So it is moving like this. This is the capital omega, okay? So it is moving like this, and 1 revolution takes 4 seconds. And just use it here, 1 revolution per 4 seconds. Then 1 revolution is given with 2 pi radian. then omega is given with 1.57 radian per second. Put also this information here, then you can calculate angular speed of flywheel 2,600 revolution per minute. And just compare the rotation of the flywheel and angular speed of the precession. So what was the omega? Omega is given with 1.57 radian per second. Okay, this precession angular speed around this pivot. And what about omega? Omega is huge. In 1 minute, it has 2,600 revolution. Okay. So with this transparency, I finished the chapter 10 and I finished the dynamics of rotational motion. As I told you before, in order to understand the rotational motion, dynamics of rotational motion, first of all, you have to understand the chapter 9, and then you can continue to study the topics discussed in chapter 10. So take care of yourself. Bye-bye.